Imagine standing on the edge of a ticking time bomb, one that's been simmering beneath our feet for millions of years. That's Yellowstone National Park, not just a haven for geysers and wildlife, but home to one of Earth's most powerful supervolcanoes. Today, we're diving into the wild idea of stopping it. Could we really prevent a cataclysmic eruption? Or is it truly an impossible mission? Let's explore the science behind Yellowstone and why taming this beast might be beyond human ingenuity. First, what makes Yellowstone a supervolcano? Supervolcanoes aren't your typical cone-shaped mountains like Mount Vesuvius. They're massive calderas, giant depressions formed when a volcano collapses after a colossal eruption. Yellowstone's caldera spans about 30 by 45 miles, hidden under forests and hot springs. It's fueled by a hotspot, a plume of hot mantle rock rising from deep within Earth, melting the crust above. This hotspot has been active for at least 17 million years, migrating as the North American plate moves over it. Yellowstone has erupted 3 times in the last 2.1 million years, each blast qualifying as a volcanic explosivity index of 8, the highest level. The most recent, about 640,000 years ago, spewed 240 cubic miles of ash, enough to bury Texas under 5 feet of debris. Ash clouds would have darkened skies worldwide, triggering a volcanic winter. Temperatures could plummet, crops fail, and civilizations struggle. If it happened today, the immediate blast zone would devastate the American West, with pyroclastic flows racing at hundreds of miles per hour, incinerating everything. Ash would blanket the Midwest, collapsing roofs and choking engines. Globally, it could cool the planet by several degrees for years, disrupting agriculture and leading to famines. But don't panic. Yellowstone isn't due for an eruption anytime soon. Scientists monitor it closely with seismographs, GPS, and gas sensors. The Yellowstone Volcano Observatory reports subtle ground uplift and earthquakes, but these are normal for an active system. The odds of a super eruption in our lifetime are about 1 in 730,000, less likely than an asteroid strike. Still, the what-if lingers. What if we could intervene? That's where the impossible mission begins. The core challenge is pressure. Beneath Yellowstone lies a magma chamber, a vast reservoir of molten rock heated to over 1,400 degrees Fahrenheit. As magma accumulates, pressure builds until the crust fractures, unleashing hell. To stop an eruption, we'd need to relieve that pressure or cool the magma. Sounds simple, right? Not so fast. One idea floated by scientists is drilling into the chamber to vent heat and gases. Think of it like poking a hole in a pressure cooker. In 2009, NASA reportedly considered a plan to drill boreholes around Yellowstone, pumping in cold water to extract heat, potentially generating geothermal energy as a bonus. The water would circulate, cooling the magma over time. But here's the catch. The magma chamber starts about 3 to 6 miles deep. Drilling that far is feasible. We've done deeper for oil. But injecting water risks triggering earthquakes or even hastening an eruption by fracturing rock. Water and magma don't mix well. When cold water hits hot rock, it can flash to steam, causing explosions. Remember the 2018 Kilauea eruption in Hawaii? Similar hydrothermal blasts occurred. At Yellowstone, a misstep could destabilize the system. Plus, the scale is enormous. The magma body is estimated at 10,000 cubic miles. Cooling it would require trillions of gallons of water over centuries. NASA's concept was more about long-term risk reduction than immediate prevention, and even they called it a multi-billion-dollar generational project. Another wild proposal, explosive decompression. What if we used controlled blasts to fracture the crust and let magma ooze out slowly like deflating a balloon? This mirrors ideas for averting asteroid impacts but flipped for volcanoes. However, blasting near a supervolcano is suicidal. Seismic waves could propagate, triggering swarms of quakes and potentially awakening dormant faults. Yellowstone sits in a tectonically active region, intertwined with the Rocky Mountains geology. One wrong move and you might cause a chain reaction. Then there's the geoengineering angle, seeding the atmosphere or crust with materials to solidify magma. Some theorists suggest injecting sulfur compounds to promote crystallization, turning liquid magma into solid rock. But magma chemistry is complex, involving silicates, volatiles like water and carbon dioxide, and minerals like quartz and feldspar. Altering it artificially could backfire, creating more viscous magma that builds even higher pressure. Think of it as clogging the volcano's throat, leading to a bigger boom. Why is all this impossible? Scale and unpredictability. Human engineering excels at bridges and spaceships, but Earth's interior is a black box. We can't model every variable perfectly. Computer simulations like those from the University of Oregon show that supervolcano eruptions are driven by buoyancy, magma rising because it's less dense than surrounding rock. Stopping that is like halting continental drift. Plus, ethical dilemmas abound. Who decides to tamper with a natural wonder? Environmental impacts could be severe, altering ecosystems that rely on geothermal heat. Instead of stopping it, science focuses on prediction and preparation. The Yellowstone Volcano Observatory uses INSAR, interferometric synthetic aperture radar, from satellites to detect millimeter-scale ground deformation. Tilt meters measure slope changes, and gas analyzers sniff for rising helium or carbon dioxide, signs of magma movement. AI algorithms now crunch this data, forecasting unrest with greater accuracy. If unrest escalates, evacuation plans kick in. The U.S. Geological Survey has zoned risk areas. The caldera for total destruction, surrounding states for ash fallout. Federal agencies coordinate with states for supply chains, air traffic rerouting, and food reserves. Globally, the volcanic ash advisory centers would track plumes to protect aviation. Remember the 2010 geological eruption that grounded European flights? But preparation has limits. A super eruption's aftermath could last decades. Ash would fertilize soils eventually, but short-term, it'd devastate farming. Studies from the 1815 Tambora eruption, which caused the year without a summer, show crop failures leading to starvation. Modern society, with its just-in-time supply chains, is vulnerable. Climate models predict a 3 to 5 degrees Celsius drop for years, exacerbating food insecurity. Yet there's hope in adaptation. Renewable energy could buffer power grids, vertical farming mitigate crop losses, and international aid networks distribute resources. Research into resilient crops, like those engineered for low light, is underway. Looking beyond Yellowstone, other supervolcanoes like Toba in Indonesia or Campi Flegrei in Italy pose similar threats. Toba's eruption 74,000 years ago nearly wiped out humanity, reducing our population to a few thousand. Studying these helps refine models. In the end, the mission to stop a supervolcano isn't just impossible, it's a reminder of our place in nature. We can't conquer Earth, we must coexist. Yellowstone's beauty stems from its power. Old Faithful's geysers, bubbling mud pots, vibrant hot springs, all symptoms of the magma below. By monitoring and preparing, we honor that power without hubris. So next time you visit Yellowstone, marvel at its wonders, but remember the fire beneath. Science teaches us humility in the face of such forces. If you enjoyed this dive into volcanic apocalypse, subscribe and hit the bell for more earth-shaking content. What natural disaster should we tackle next? Let me know in the comments. Stay curious and stay safe.